Day 151, Honors Physics, Magnetic Field Strength. Basically, the goal is to learn how to measure and draw magnetic fields. In other words, how do we know that one magnet is stronger than another? And then what units do we use? And then how do we draw these magnetic fields? And it comes down to some of the challenges we have in physics all the time. We're dealing with stuff that is invisible, and it's three-dimensional, and we are dealing with a visible two-dimensional piece of paper. So we have to do a lot of visualization here. Once again, I like to call it theater of the mind. But we have some tools that are accepted conventionally, internationally, to help us out here, some pretty good rules. And with practice, you should get pretty good at understanding these diagrams. The bottom line is, as you sit in the room you're in right now, you are in a magnetic field, at least one magnetic field. It's the magnetic field of the Earth. And that magnetic field of the Earth fills your room. If we are in my actual physics room right now, the magnetic field of my room, we could prove it's there, because all you have to do is take out a compass, and you put a compass, a little magnetic compass, the old school compass with a little needle, anywhere in a room, it'll point north. And the front of my room, where the smartboard is, happens to be towards the geographic north, which is for the most part lined up with the magnetic direction of north, which is the actual, as we learned in the last lesson, the south magnetic pole of the Earth. But bottom line is, the magnetic field in the room, in my room at school, points toward the north, and any compass anywhere in that room will point that way. Magnetism fills that room. It's invisible. You don't feel it, but you can detect it with a compass needle. So, I kind of go back to the fundamental source of magnetism. Where does magnetism come from? Well, it comes from the movement of an electric charge, and the most basic electric charge is an electron, and we have protons, but electrons are easier to come by for reasons we've talked about before. They're loose. Protons are in a nucleus. They're hard to get a hold of or to separate, but electrons are always in motion, orbiting. They're also spinning, and both those types of motion creates magnetism around that electron. Here we have a wire in this diagram, and I'm going to explain this diagram as we go along here, but we have a wire. This is representing a wire with electric current in it. It's attached to a battery or something. They're not showing all the other wires that connect it to the battery. But when the current flows in a wire, you get a magnetic field that circles around that wire. So all these circles here represent magnetic field going around that wire, and these are like little compass needles. Once again, it's supposed to be a three-dimensional diagram on this two-dimensional piece of paper, and there's a little bit of confusion possibly about the way it's drawn there, so we're going to simplify this diagram in a few minutes here. Let's go back to the top of the page here. So why does that magnetic field surround that wire? Why? Well, it's because moving charges create magnetic fields. When you have current in a wire, it's moving electrons. Could be moving protons, but we know it's not protons, it's electrons. So we go with the convention, the international conventions here. For example, in this diagram, we have current going towards the up. Now, up is a little bit vague at times, so we have to be a little bit more specific, because we could have up towards the sky, we could have up towards the top of this page. I'll probably use that word, but we try to stay away from it as best as possible. Same thing with down. Down could be towards the bottom of this page or towards the floor, so we'll be more specific as we go along here. But we have this thing called the right-hand rule. And basically, you can see this hand down here near the bottom, and you kind of make a fist with your thumb sticking out, kind of like you were a hitchhiker. Back in the olden days, we used to hitch rides like that. Don't do that now, obviously. It's not safe. But what you do is you imagine yourself grabbing that wire. Here's an arrow in this diagram down here that represents the wire with the current going towards, let's say this wire is laying on the piece of paper on this table. It'd be like a pencil laying on a table with the pencil point pointing towards the top of this page, the front of the room you're sitting in. Well, if that pencil or that wire lays on that table, if you were to grab that pencil with your hand, your right hand, your fingers curl around. They represent the magnetic field. Your thumb represents the way the current is flowing. Essentially, you get either clockwise or counterclockwise, but that's not always a really good way to describe it with clockwise or counterclockwise, but it's kind of being shown in this diagram here. Another thing to keep in mind, as you'll see in the next part of this, is that The closer you are to the wire, the stronger that field is. That's when we're going to measure these. But there's two objectives today, is to measure, get a numerical number, quantitative number, to give you the size and strength of a magnetic field, but also to represent them. So this diagram we have here represents magnetic field. It's one way to do it, but it's not the overall most concise way to do it. So people got together in the olden days to come up with a more consistent way to draw magnetic fields that are more descriptive and have greater clarity, so to speak. Up here at the top, what they do, because we have three directions that we're trying to indicate on a piece of paper. Like on a piece of paper, you have to the right and to the left. If you're doing a map, a flat map, that's east and west. And then on a piece of paper, you have like north and south, or towards the top and towards the bottom. So you have those four directions, like in the XY graphing plane. But if you have three-dimensional space, now you have also like towards the floor or towards the ceiling. So the way we deal with that up here at the top, what they do is, or what we will do, which is an international convention, if you draw a little circle with an X in it, that means into the page or towards the floor. If you draw a circle with a dot in it, that means out of the page or towards the ceiling or towards the sky. So that's towards the sky. This is towards the floor. So to put that all together, for example, with the original wire we have over there on the left-hand side, if we have that wire with current going this way, there's the wire laying flat on the table, like a pencil laying there, like a pencil with its point pointing towards the front of the room, towards the top of this page. It's laying in that plane. The magnetic field circles around that wire. And here's how we draw that. I'm going to switch colors here to help us out. So the blue now I'm going to draw is going to represent magnetic field. And if I draw a bunch of circles here, and I'll explain this, I'm going to draw smaller circles. I'll do it on both sides. And I've skipped ahead a little bit here, so you might have to pause. But on the right-hand side here, these circles with the X, that's where the magnetic field would go down into the page, but circles don't have a single direction. Those X's that I have over here on the right-hand side right now represent tangents to circles that circle around this wire. Because the magnetic field goes perpendicular to the page only at that tangent spot as those circles go around that red wire. Then those circles go around under the wire and come back up and then tangent towards the ceiling when it comes out on the left side of this wire. So on the left side of this wire, you would put dots representing tangents to the circular magnetic field circling that wire. Now the reason why I have smaller circles the further you get away from this wire is that represents the magnetic field getting weaker the further you get from that wire. So I've drawn a second example over here on the right. So I have a wire with current going down towards the left over here. So once again, as current flows, and if there's no current in the wire, there's no magnetic field around the wire. But if you were to grab that wire with your right hand and your thumb pointing in the direction, so that's say a pencil laying on your table, your fingers would poke through the paper right here. If they could go underneath that wire, if the wire is stuck on the piece of paper, they would poke through here, tangent to circles, and then they would come back out over here as your fingers curled around those wires. So I would draw the magnetic field to look like the following. So you might need to pause this video again, and there's nothing magical about green. I'm just trying to show you it's a different diagram than the other diagram. Those symbols that I put there represent tangents to circles, the circular magnetic field that circles around that wire. And it fills all the spaces even between the circles. The magnetic field is, it weakens with distance, but it fills all of space. That you just can't draw, a million more circles with X's in it. You don't need to. But the magnetic field fills all of space, just like the magnetic field of the Earth fills the room that we're in right now. And it would be all straight towards the front of the room if you were able to draw that, which we're not going to do right now. But once again, also, the smaller circles represent the weakening of the field as you get further from the wire. Okay, now for the math part of this, which tends to be the easier part in a sense because it starts off basically plug and chug. Calculating numerical strength. How strong is one magnetic field versus another? How do we know when one magnet is stronger than another magnet? The magnetic field is the space around the wire. So we have this equation that I filled in for you, and we have one symbol that's new, this mu zero. This is mu zero. It looks like this. It's the permeability of free space. It's kind of like pi. It's not pi. Pi is in this equation as well. Pi is 3.14. It does not have units. But it's a constant that you'll be given, so you don't need to memorize it. In fact, the value for mu 0 over 2 pi, is given right down here. That will always be given to you on the test. So you'll be using that number, 2 times 10 to the negative 7th newtons per amp squared, when you do these calculations. The main thing is a couple other things. I is the current in the wire. The stronger the current, the stronger the magnetic field. R is how far you are from the wire. And then the new thing here, besides mu 0, is this B. The capital letter B is that is a letter that we use. It's internationally accepted as the symbol for magnetic field strength. How strong a magnetic field is. Now, magnetic fields are measured in Teslas. They can also be measured in Gauss. But Tesla, you've heard of that. And the car, well, you saw the video on Nikola Tesla, and the car is named after that. All of those are related from the same person in honor of Nikola Tesla. A Tesla is a Newton per amp meter. You don't need to know that either, but it's useful. It'll be more useful next year when and if you take AP Physics. But bottom line is you have to have your current in amps, your distance in meters, and then the magnetic field strength comes out in Tesla. So you could have a 5 Tesla strength magnetic field. So let's start off with an example problem here. Calculate the magnetic field strength at a distance of 2.5 centimeters from a wire of 6.0 amps. So I'll just plug that in. And that comes out to be 4.5 times 10 to the negative 5th Teslas. Making sure that you have meters. The 2.5 centimeters is 0.025 meters. Once again, you might need to pause that to write everything down there. And then for the direction, you'd need more information about where your wire is, and you would draw those diagrams like we have at the top, and we'll practice that some more in a little bit. One thing at the bottom here that won't be emphasized this year, but I just want to introduce it now. The flow of magnetic field through space is called flux, and flux is measured in Webers. We're not going to do anything in Webers this year, but just want to kind of introduce that idea. You're sitting in a room right now that's filled with a magnetic field, and we say the magnetic field, it might be, I forget what the strength of the Earth's magnetic field is. It might be 4.5 times 10 to the negative 5th Teslas. I'm not sure what it is. I'd have to look it up. Let me do that real fast. Yeah, so I just looked it up, and the Earth's magnetic field is around that. It does fluctuate quite a bit. It says that it's somewhere between, say, 2.5 to 6.5 times 10 to the negative 5th Teslas on the surface, depending on where you are. And if you go higher, it's different. In different areas, it's a little bit different. It varies quite significantly, but that's in the range of how strong the Earth's magnetic field is at the surface. But anyways, flux is the flow of magnetic field through space. Put that in your back pocket for now. You won't need to know that. We'll come back to that next year.